All right, let's dive into one of the greatest detective stories in the history of science. We're going on a journey to figure out what the building blocks of you, me, and everything else in the universe, atoms, actually look like. It's an incredible story, full of twists, turns, and ideas that literally changed how we view reality itself.
So let's start with the big mystery. What does an atom really look like? If you could somehow shrink down, way, way down, past what any microscope can see, and look at a single atom, what would you find? That's the question that scientists have been obsessed with for centuries.
For a really long time, the best idea we had came from a guy named John Dalton, way back in 1808. He said an atom was basically the smallest possible thing, a tiny, solid, unbreakable ball, like a microscopic billiard ball. And that was it. Simple, right? Well, that simple idea was about to get completely smashed to pieces.
So it turns out that little unbreakable ball wasn't the end of the story, not even close. Scientists were about to find out that the atom itself was made of even smaller parts, turning it from a simple ball into a complex puzzle.
The first major crack in the case came when J.J. Thomson discovered the electron. He found these incredibly tiny particles with a negative charge. Now think about it. If an atom could spit out these negative pieces, then it couldn't just be one solid, indivisible thing. Suddenly, the whole game changed. The question wasn't just, what is an atom? It was, what's inside an atom?
So, over the next few decades, the rest of the crew was discovered. You've got Thomson's electron, which is super light and has a negative charge. Then you've got the proton, discovered by Rutherford. This one's a heavy hitter with a positive charge. And finally, you have the neutron, found by Chadwick. It's about as heavy as a proton, but as its name suggests, it's neutral, no charge at all. These three became our core building blocks.
Okay, so finding the pieces is one thing. But now you've got an even bigger puzzle. How do they all stick together? You've got positive stuff and negative stuff. Are they just all jumbled up in there? Is there some kind of order to it all? The race was on to draw the first blueprint of the atom. And this next chapter is all about trying to visualize something that no one can actually see. You can think of these first attempts as rough sketches, the very first drafts of what an atom might look like based on the clues they had.
J.J. Thomson, the guy who found the electron, took the first shot. He came up with what we now call the plum pudding model. Just imagine a chocolate chip cookie. The cookie dough is like a big, soft ball of positive charge, and the tiny negative electrons are the chocolate chips scattered throughout. It actually made a lot of sense at the time. It kept everything balanced and was nice and simple.
But here's where things get really cool. An experiment led by Ernest Rutherford was about to completely blow that cookie model out of the water. His team was firing these tiny positive particles at a sheet of gold foil that was unbelievably thin, and the results were just shocking. Rutherford himself said it was as surprising as if you fired a cannonball at a piece of tissue paper and it bounced right back and hit you. The plum pudding idea just couldn't be right.
To explain this bizarre result, Rutherford proposed a new model that was totally radical. He suggested that almost all the atom's mass and all its positive charge were crammed into a tiny, dense point right in the center, which he called the nucleus. The only way those particles could bounce back is if they hit something small but incredibly solid. And the electrons? He figured they must be orbiting way out on the edges, like planets around a sun. So let's just compare these two. Thomson's model is basically a solid blob. But Rutherford's model is, well, it's mostly empty space. You've got this tiny little nucleus, and then this huge, vast emptiness with the electrons zipping around on the outside. This was a revolutionary way of thinking about matter.
But there was a huge, glaring problem with Rutherford's model. According to the physics everyone knew back then, an orbiting electron should be constantly losing energy. And as it loses energy, it should spiral inward, faster and faster, until, bam! It crashes into the nucleus in a split second. But atoms are stable. The chair you're sitting in isn't collapsing. So what was going on?
The solution came from a physicist named Niels Bohr, and his answer required a completely new and frankly very weird set of rules for how the universe works. Welcome to quantum mechanics.
Now, to understand Bohr's big idea, you have to get your head around this concept of quantization. Basically, it means that in the tiny world of atoms, energy isn't like a smooth ramp you can stand anywhere on. It's more like a ladder. You can be on the first rung or the second rung, but you can never, ever be floating in between the rungs. Energy only exists in these specific bite-sized packets.
Okay, so here's how Bohr brilliantly solved the spiraling electron problem. First, he said electrons are only allowed to exist on specific orbits, like the rungs of that ladder.
Second, and this was the crazy part, he just declared that as long as an electron stays on one of those rungs, it just doesn't lose energy. It breaks the old rules. And third, electrons can jump up to a higher rung if they absorb the exact right amount of energy, or they can fall down to a lower one by spitting that energy back out as light. And Bohr's model was a huge success. For the hydrogen atom, it worked perfectly. It explained so much. But it wasn't the final answer. When you tried to apply it to bigger, more complicated atoms, the math just didn't hold up. The story of the atom had one more, even stranger twist to come.
So this brings us to our modern view, the quantum mechanical model. And this is where our picture of the atom stops looking like a tiny solar system and starts looking more like a fuzzy, ghostly cloud of pure possibility. The final piece of the puzzle comes from Werner Heisenberg and his famous uncertainty principle. What it says is a fundamental law of the universe. You can never know both the exact position and the exact momentum, like where it's going, of a particle like an electron at the same time. The more you pin down one, the fuzzier the other becomes. And that single idea makes those nice, neat orbits impossible. They just can't exist. So if we can't know where an electron is and where it's going, what can we know? Well, we have to give up on the idea of a path altogether. Instead of an orbit, we now talk about an orbital. And an orbital isn't a line the electron follows, it's a 3D region of space, a probability map that tells us where the electron is most likely to be found.
Here's a look at the simplest orbital. It's called an s orbital, and it's just a fuzzy sphere. Now, this doesn't mean the electron is flying around inside the ball. It means that if you could take 1,000,000 snapshots of the atom, most of the time you'd find the electron somewhere inside this spherical cloud.
And believe me, they get much weirder. These are p orbitals. They're shaped like dumbbells. And again, these are not flight paths. They're just maps of probability. So the atom isn't a tiny solar system after all. It's this beautiful and bizarre collection of probability clouds.
And that leaves us with one final mind-bending question. We've just seen that every atom is almost entirely empty space, governed by the strange rules of probability. So why does the world feel solid? Why can I knock on a table? Why doesn't my hand just pass right through it? The answer has to do with the forces these probability clouds exert on each other. But that is a story for another time.